All right, any questions? Yeah.
I'm having a weird issue, like, I need help, and I don't know how to debug it. And it's, whenever I enter a valid plate, it returns someone about the wrong name.
Is it always the same wrong name?
It's always the same wrong name if it's the same plate. So like if 1, 2, 3 is supposed to be John, and 1, 2, 3 it always do Howard.
But a different plate is a different wrong name?
Yeah.
Well, that's interesting. Is this before you do any deletions or anything?
Yeah, and I know, but when I do dump, it's all correct.
Okay. I'm gonna guess that when you do a search, maybe you're not doing your scanf correctly.
Okay.
That you're copying it into some other variable than plate or something simple like that.
Okay.
But catch me after class if you want. I got a few minutes after class today. And we can run through it together in the debugger. All right, other questions?
How you doing?
Doing well. Thank you. How are you?
Doing pretty well.
Cool. It's spring out there, man.
It is?
I mean, stuff has been blooming for months, but all of a sudden everything's exploded. Cherry blossoms are out.
I'm pretty happy that when I'm leaving electricity which is on August 1st, that there's actually still some sunlight.
Yeah, that's always nice.
Which is pitch black.
Mm-hmm.
It's gonna be like nice for a few days, and then it's gonna be back to rain and cold.
Yeah, yeah.
April.
I don't mind the rain. I'm happy for the warm weather, though. All right, so I checked a little while ago, and I've only got like 22 GitLab repos for PA5. So please make absolutely sure you push your repo over and set me up as a reporter, okay, before 8 o'clock tomorrow. I'll download everything at 8 tomorrow morning and start grading from there. So even if your code's not finished, push the repo over there, right? Just to have it there. All right, so let's talk more about dynamic programming. We started playing with this idea of a knapsack problem yesterday. So there's a bunch of different knapsack problems, but the general setup is always the same, right? You have something like a bag that has some sort of limit on its capacity, so it might be able to hold only a certain number of pounds of stuff. And you're trying to put things into your bag in a way that gets you the maximum value of stuff in your bag. Okay? And there's different versions of this problem. Let me give you one example. You have item A, and let's say we have our weight and our value. And maybe item A, every pound is worth $5. And item B might weigh 2 pounds and be worth $8. And item C might be 4 pounds and is worth $25. Yeah. Thank you. And let's say your capacity of your bag is 10 pounds. Okay, if these are, food in bins at a bulk food section of the store, and you can take any amount of these things that you want, there's a pretty easy algorithm for maximizing your capacity. What should we take to fill up a 10-pound capacity bag? You can calculate your value per weight. And item A is worth $5 a pound. Item B is only $4 a pound. Item C is, $6.25 per pound. This is the most valuable item. So let's take 10 pounds of item C. We're done. Okay, that's a pretty easy algorithm because we're allowed to take however much of this item we want. In this case, 2.5 of item C. Right, to get 10 pounds out. A slightly more challenging case is when you have a limited amount of these items available. For example, maybe we only have 8 pounds of item item C and only 1 pound of item A and 10 pounds of item B. Well, how should we pick our items and put them in our bag to get our maximum value, assuming we can take fractional amounts of these things? What would be our best solution here?
Just take the most expensive item and build it out. And then
Yeah.
take the next most expensive item.
So take 8 pounds of item C, and now we have 2 pounds of capacity left. Well, we could take 1 of item B or 2 of item A. Item A is worth a lot more per pound. It's worth $5 a pound instead of $4. So we'll go ahead and we'd like to take 2 pounds of item A, but there's only 1 available. So take 1 pound of A, and now we have 1 pound left, and the only item we can choose from is B. So take half of an item B, 1 pound of B. And that's guaranteed to get you your best solution. And we can prove that in an algorithms course. You would prove that in class usually. So this algorithm we're using is an example of what's called a greedy algorithm. And it's greedy in the sense of classic greed, right? Greedy mindset, you want as much as you possibly can have right now, right? Just give me the money, give me the goods. That's how this algorithm is working. It's saying, you know, if I start taking a bunch of item C, that gets me the most value per pound. Give me as much of that as you can until I fill up my bag or I run out of item C. Well, in this case, we ran out. How do we satisfy our greed? Well, what's the next most valuable item? Give me as much of that as you can, right? And a greedy algorithm works perfectly well for this particular problem setup. And there's lots of algorithms that work well with a greedy approach. So if we're trying to find shortest distance through a graph, we can use something called Dijkstra's algorithm. And that's a greedy algorithm, and it works really well. So there's a variation of the knapsack problem where we're not allowed to take fractional amounts, where we have to take whole numbers of each item. So these aren't, you know, pounds of something where we can take 2.5 pounds. These are indivisible items. And so this is sometimes called the 1-0 knapsack problem. Because you take an item or you don't take it. And the 1-0 knapsack problem is harder to solve. And a greedy approach doesn't work. So let me give you a different weight table. So let's say item A weighs 1 pound and is worth $1. Item B weighs 3 pounds and is worth $6, and item C weighs 4 pounds and is worth $9. So this is $1 per pound, this is $2 per pound, this is $2.25 per pound. So C is our most valuable item, and then B, and then A. So suppose our bag can hold 4 pounds worth of stuff. What's our best way to fill the bag to get the maximum value? So for the A would be 4 pounds, that would get me $4 worth of stuff. Is there a solution that's better? So C, 4 pounds, gets me $9 worth of stuff. I could do a B and an A, that would get me 6 plus 1, that would get me $7 worth of stuff. So here the best solution is C, and our total value is equal to 9. And that's what a greedy algorithm would give us. All right, if our capacity is 5, what's our best solution? Yeah, C and A. So one of C and one of A gets us a value of 10. And the only other possibilities would be we could do a B and 2 A's. That would get us 6 plus 2 is 8. We could do 5 A's, that would get us 5. Those are worse than this, which gets us 10. And so that's again a greedy solution, right? We took the most valuable item. We couldn't take another one of those. We couldn't take any of the second most valuable items, so we filled up with the third most valuable item. But this changes when we get to a capacity of 6. So what's our best solution here? Because if we start off by taking item C, that leaves us with 2 pounds. Our only way to fill the last 2 pounds is 2 of item A. That would give us $9 plus 2 is 11. But if we do 2 of item B, that gets us 12. And if we do 6 of item A, we only get 6. That's not going to be the best. So here, the best solution is not to be greedy. We have to somehow look ahead and say, oh, we should take B, even though it's worth less per pound, because we get to use more of the capacity. And we can still fill our 6 pounds by filling in with A, but the price penalty of A versus B is greater than the extra gain we get by having the slightly more valuable item in our bag. So the question is, how can we code a function, how can we describe a function that will tell us what the maximum value is we can get from a bag, given a pricing table and a capacity? And greedy approach won't work, but we can come up with a recursive definition of this function pretty easily.
Can you do a comparison between the highest value of your weight and then compare it to the capacity values?
What would you be looking for in that comparison? Right, because C is definitely the most valuable per weight, but it's actually not part of our best solution for that case. Because there's the flip side, which is that, yeah, this is a nice valuable item, but the amount of weight that's left is only enough to fill up with this very unvaluable item, right, which is half as valuable as item B.
So can you compare the weight versus the pricing? Like, do the sum and then compare those two, or is that like inefficient?
You can, but it gets a lot worse if there's more than just 3 items here, right? So we need to start looking at all those combinations. So yeah, you're on the right track. We just want to find an algorithm that sort of captures that. Yeah.
Would part of it be checking what gives the maximum value for maximum weight divided by item weight multiplied by value per weight?
That works sometimes, but there's cases where that actually doesn't get you the best solution.
Okay.
So let me give you a pretty simple way to look at this algorithm, this function, and pretty easy to code, but pretty complex computationally. The computer ends up doing a lot of work, but we're okay with that, right? So let's define a function called maxval, which takes an argument which is called capacity. And this is the maximum value we can get from a bag of the given capacity. And we're going to write this recursively. So a base case is if the capacity of your bag is 0, you can't put anything in it, so the most you can get out of that bag is 0. So that'll end our recursion. Otherwise, we have to do a few calculations. And these calculations are based on the idea that whatever gives us our maximum value, whatever collection of items, right, We can start with whatever particular item we want, but we're going to put a first item into the bag. Okay, we're going to start with an empty bag. We're loading items in. Let's just think about the first item we put in our bag. Okay, and it's going to be one of the items in our inventory. We don't know which one. But what we can do is we can say, suppose I put the first item in. If I can calculate the maximum value that I get by starting with item A, and I can calculate the maximum value I get by starting with B, or starting with C, or starting with D, or starting with any of those items, I can just take the largest of each of those calculations. That's my maximum value. Because whatever my solution is, I'm going to start by putting some item into my bag. So let's do this as the maximum of a number of possible things. Suppose I put item A, let me call it item 1. Suppose I put item 1 into my bag. Okay, whatever item 1 is. Two things happen. First thing that happens is my bag now holds a certain amount of value. Okay, in particular it holds the value of item 1. But since I put item 1 into my bag cannot hold as much stuff anymore. I've diminished the capacity of my bag. How much have I diminished it by? Whatever the weight of item 1 is. So I put item 1 in my bag. I get this much value from that item. My capacity goes down by the weight of item 1. How much value can I get from a bag with this diminished capacity?
They would call it stuff on the new maximum capacity.
Yeah, let's just use the max val function. So max val of this diminished capacity. Well, if I take that maximum value I can get from this bag that holds less and I add the value of the first item I put in my bag, that's the maximum value I can get if I start by putting item 1 in my bag. On the other hand, I might have started by putting item 2 in my bag, in which case I would get the value of item 2 plus the maximum value I can get from a bag whose capacity has been diminished by the weight of item 2. And same for item 3 and same for item 4 up through item n. So if I have n items in my inventory, I calculate these n possible answers. I pick the largest. That's my max value. And that's a perfectly fine recursive definition. And there is one caveat here. Don't consider any row where the weight of the item is bigger than the capacity. In other words, if my capacity is down to 5 pounds and item 2 weighs 10 pounds, I can't say the value of item 2 plus the max val of capacity of minus 5. All right, that's meaningless. Because if my capacity is 5 and my item weighs 10 pounds, I cannot put that item in my bag. So I'm not allowed to consider this value in calculating my maximum. So if you're finding the maximum by iterating over a for loop and keeping track of the max at each point, right, you only consider values where, items where the weight is less than or equal to the capacity that you're working with.
Would it be efficient to implement this as like a tree where you just traverse the left side of the tree, or is that kind of...
It really is a tree, right? And you really are traversing it. And you have to kind of traverse all possible paths down to a leaf in order to find the max. But what we're going to see is that the tree is really, really big. right? And trying to traverse it is going to be pretty combinatorially explosive. But that's basically what we're doing with this. It really is a tree and we're traversing it. But let's write this out in a particular case and see what happens. Does this basic algorithm make sense? All right, so let's run through this with our particular inventory. So let me make a table up here. So here's our item, here's our weight, here's our value. And the weights are 1, 3, 4, and the values are 1, 6, 9. So there's our inventory. And let's find max val of 6. Well, the maximum value we can get out of 6 is the largest of the following 3 quantities. If we put item A in, we get a value of 1. And since item A weighs 1 pound and our bag can hold 6, after we put item A in, we now have a bag that can only hold 5 pounds. And so if we want to know what's the most we can get from that, that's just max val of 5. Or we could choose to put item B in, which is worth $6, weighs 3 pounds, which means it leaves us with a bag that can only hold 3 pounds. Or we could put item C in, which is worth a whopping $9 and diminishes our capacity by 4 pounds, which means we can only put 2 pounds in our bag. So if we can calculate those 3 values, we can just take the largest of those 3 sums. That's our max val of 6. Okay, if you understand that one line, you understand the knapsack problem solution. So this is the usual drill. You find a friend who can solve the knapsack problem for values less than 6. You ask him to solve these 3 problems, and using those you can solve the problem for 6. Well, let's keep going. So max val of 5 is the largest of item A would be 1 plus max val of 4 pounds left. Or it could be 6 plus max val of 5 minus the weight is 3, that's 2 pounds left. Or it could be 9 plus max val of 1 pound left. We'll need to calculate max val of 4. So if you go with item A, that's 1 plus max val of 3. Or we could put in item B, so that's 6 plus max val of 1. Or we could put in item C, that's 9 plus max val of 0. Now this turns out we're going to end up computing every single max val from 5, 4, 3, 2 down to 1. That's happening because we have an item whose weight is 1. If the smallest item had a weight of 7, right, then we would have jumped from, say, 100 down to 93 and so on. So you may not end up calculating every single max val between 0 and your target, but in this case we are. So it's a good illustration. So put in item A, that's $1 plus max val of 2. We could put in item B, that's $6, and it leaves us a capacity of 0. If we try to put in item C, our first version of the code would say, well, that's worth $9 plus the max val we can get from a bag that holds minus 1 pounds, but that's not physically meaningful. So we need to not consider this possibility. Because if your bag only holds 1 pound to start, we can't say, well, I could get $9 plus the capacity of a bag that holds minus 5 pounds. right? We cannot put item C into a bag that only holds 1 pound, or 3 pounds in this case. So we're not allowed to consider this. So here we're just finding the maximum of 2 possibilities. So that's just an if statement you put in your for loop. So if it holds 2 pounds, we can get $1 plus max val of 1. And again, we cannot put item B, which weighs 3 pounds, in a bag that only holds 2. And we definitely can't put item C, so we only have one possibility. And then max val of 1 equals, put in a pound plus the remaining capacity of 0. And eventually we're going to call max val of 0. And that's just going to be 0. That's a base case which does not recurse. Okay. The base case says if our capacity is 0, just return a 0. So that's where we start coming back up out of the rabbit hole. And once we have max val of 0, that'll let us calculate max val of 1, and that'll let us calculate max val of 2, which gives us this value. And then we would make another call to max val 0, which would return a 0, which would give us this. That gives us max val 3. That gives us this first part of this calculation. And then our code would say, okay, let's calculate max val of 1. And it's going to go off and it's going to try and find max val 0 and so on. Okay? This is this recurring subcase structure that we saw with Fibonacci's. All right, by the time we get to max val 6, we're going to do all this work. This is all just to find max val of 5. And then it's going to say, okay, let's find max val of 3. Which is going to say, okay, well, I need to find max val of 2 and 0, and to find 2, I need to find 1, and so on. It's going to do all that work again. And then we're going to try to find max val of 2, and it's going to do all of this work. Okay, as this inventory gets larger, the amount of work we're doing gets really, really fierce. And this will run and not finish.
So what I'm kind of confused about is, because we're doing this in a for loop,
Mm-hmm.
so recursive,
So this calculation we can do typically in a for loop. We don't have a max function that you can throw an arbitrary number of things into. But we can, right, there's basically one possibility for each item in your inventory. So we do something like, best answer is 1 plus, value of item 1 plus max val capacity minus weight 1. And then we'd loop from 2 down to the last item, calculate each of these, and if it's bigger than our best answer, set the best answer. At the end of that for loop, best answer will be this max. Okay? But within that for loop, right, each of these calls is going to be a big recursive call. So yeah, the topology of it is all twisted together. All right, so we make this tractable by using dynamic programming. Remember, dynamic programming is just the idea that every time we calculate the value of this function, we're going to save it somewhere. And then the next time we want the value of this function, we'll see if we've already calculated and saved it. And if we have, we'll just take the saved value instead of actually going through this whole process. So if we were calculating max val 10 and at some point it needed max val 6, the first time it has to do that, this is all the work it's going to do. But if later on it wants to know something that involves max val 6, we've already calculated this and saved it, it'll just read the value from memory. Okay, so I'm going to simulate that with a pen. I'm going to write down the value of each of these max vals. And every time we need a max val, if it's written down, we'll just use that value instead of recalculating. Okay, so max val of 0 is 0. Well, that's an easy one. And I'm going to record the inventory of items that get us our maximum value. Okay, well, if our bag holds nothing, it's just the empty set. Okay, we don't have any items. Or let me just do a 0 length string. Okay, max val of 1. This expression is the result of putting in one of item A plus whatever gets us the maximum value of 0. Okay, the maximum value of 0 is a solution that has no items added to your bag. So the result of this is just an inventory containing item A. That's how we get the maximum value of 1, and it's equal to 1 plus max val of 0. That's got a max val of 1. Okay, not terribly interesting yet, but it's true. If you have a bag with capacity 1, your best value you can get out of that is 1, and you get that by putting in 1 of item A. Okay, max val of 2 is the largest of, well, again, we only have one thing, which is what we get by putting item A in our bag first and then getting the max value out of the remaining 1 pound. Max val of 1 is 1. Max val of 2 is 1 plus 1, that's 2. And the solution we get is by putting in an item A and then putting in whatever inventory gets us max val 1, which was just a single item A. Okay, max val 3 gets a little more interesting. This first calculation is the result of putting item A in your bag. This is the result of putting item B in your bag. Max val 2 is 2. Max val of 0 is 0. So we're calculating the maximum of 3 and 6. What's the largest of those? 6. So this is equal to 6. And we got that by just putting in an item B, followed by nothing. Okay, now it starts to get fun. Max val of 4, well, this is the result of putting in item A, B, or C. So max val of 3 is equal to 6. Max val of 1 is equal to 1. Max val of 0 is equal to 0. So we have 1 plus 6 is 7. 6 plus 1 is 7. 9 plus 0 is 9. That's the largest. So max val of 4 is 9. And the inventory that gets us that is just 1 of item C. Alright, max val 5, this is putting in item A, B, or C. Max val of 4 is 9. Max val of 2 is 2. And max val of 1 is 1. So now we want the largest of 1 plus 9, 6 plus 2, or 9 plus 1. Okay, so the max val is 10. And we have two ways to do that. We could put in item A in our bag and then put in the solution for max val 4, which is a C. Or we could put in item C in our bag and then take the inventory for max val 1, which is an A. Okay, if we don't care about a particular solution, we just want a solution, I'll just take the first one. So this was an A that we put in for this first case, followed by the inventory that maximizes capacity of 4, which is a C. Same set, just a different order, right? So capacity 4, we already decided in the beginning the best way to get that was item C. That's what we got. Capacity 5, it was a C and an A. That's what we got there. All right, so what happens when we get to our real question, which is what's the maximum value from a capacity of 6? Well, max val 5 is 10. Max val of 3 is 6. And max val of 2 is 2. So now we're looking at the maximum of 11, 12, and 11. The largest of those is 12. And again, this is A, B, C. So the way we get the 12 is by putting in an item B, followed by whatever inventory results in max val of 3, which was just a B. And since that's what we were after, we have our final answer. The maximum value from a bag that holds 6 is $12, and we get there by putting in 2 of item B. And it's pretty efficient as long as you're using dynamic programming, so we're storing each of these max values as we calculate them. And you can handle a pretty big inventory, a pretty big capacity. If you don't use dynamic programming, it slows down to the point of never finishing really quickly. So I've used this for program 5 in the past. And it's not bad. The trickiest part is understanding the algorithm. But like I say, if you understand this first expression right here, you've got it. right? Everything else is just another version of this where you're starting with a different capacity. And the mechanics are a little frightening because it's C, so trying to pass around an inventory of items and keep track of the inventory, that gives you the maximum. You get into all kinds of pointers and dynamic stuff, and that can be challenging. But the algorithm itself is pretty simple because it's really just based on this one recursive definition of maximum value.
So did you say we're going to be switching to Java the last?
223 is Java. No, we're still going to do C for PA5. All right. Longest common substring. So this is a fairly classic computer science problem. This pops up in genetics. This was the first time I was exposed to it. So you have strands of base pairs of DNA. So right, there's a strand of DNA, and here's another there's another strand. They don't have to be the same length. And you know, when you sequence DNA, when you're taking a strand of this and you're trying to figure out what the base pairs are, there's noise, right? Sometimes a letter gets dropped, sometimes other letters come in. It's a physical process. And so these look, you know, very different, but they might have a subset of symbols that are common to them in the same order, right? For example, you know, this A and this A are in common. This T and this T are in common. This T and this T, this A, this C and this A. So there's a sequence of 6 characters that are common between these. There might be a different way of finding subsequences in common that's longer, right? I could have started with this A, and I could have said, well, this A matches this A, and this T, and maybe I'm going to match this A to this A, and then this A to this one, and this T over here, right? So it's an interesting question of, if you have 2 strings in general, how do you find the longest common subsequence between those 2 strings? And this is, you know, again, combinatorially expensive if we just brute force it. If we just take every possible substring from here and look for it in here, and then take the longest of the substrings that we found. But we can write this as a nice recursive definition. So longest common subsequence of X and Y. And it's just got a few possibilities. So if X and Y have the same last letter, and I don't want to get bogged down in mechanics, but let's add the length to our strings as arguments. So longest common subsequence of X with a length of X and Y with a length of Y. Okay, if X and Y have the same last character, then those characters are in common. So the longest possible subsequence would be 1 plus longest common subsequence of X, length X minus 1, and Y, length Y minus 1. In other words, if they both end with a T, ignore those, find the longest subsequence in common here, and then add 1, because they also both have a T at the end. If they don't end with the same letter, so this ends with a C and this ends with a T, well, we can now consider two other problems. The first is the longest common subsequence of this with that. And the other is the longest common subsequence of this shortened string with this original string. So we can find longest common subsequence of x, length x, y, length y minus 1, and the longest common subsequence of x, length x minus 1, y, length y, and find the largest of those. And we need a base case, which might be if one of the strings has length 0, then the longest common subsequence is 0. And so each of these will, make a recursive call to LCS with at least one argument that's smaller than what you were called with, one length that's smaller than what you were called with, which means our strings are shrinking, and after a finite number of these calls, eventually at least one of these arguments is going to be 0. That's our base case, pops us out of the recursion. And this is a really efficient way to code it up. So you can find lots of examples where this repeated common substructure pops in and where dynamic programming makes things more efficient. Okay, so let's talk about PA5, and I'll post this later on today, and we'll talk about it in more detail tomorrow, but let me give you the basic setup. We're going to be dropping eggs off of floors. Okay, so here's the deal. You have a collection of eggs, you have a building with a certain number of floors in it, and you are trying to answer the following question. What's the highest floor from which you can drop an egg without it breaking? Okay, that's the question we're after for the next week and a half. What's the highest floor you can drop an egg from without it breaking? And there's all the simplifying assumptions you would want. The eggs are identical. If you drop an egg and it doesn't break, it's not damaged. Okay? If it survives from a certain floor, you could drop it again from that floor, it's guaranteed to survive. Okay? If it survives from this floor, it'll survive from any floor below it. If it breaks from a given floor, it will break from any floor above it. Okay? Every time you drop an egg from a floor, you get exactly the same result. So there's no wind or changing conditions or anything like that. So idealized eggs, floors, and ground behavior. And the question is, what's the highest floor from which you can drop the egg without it breaking? Okay? There's no way we can write a piece of code which answers that question because we don't know anything about the physics of these eggs or how bumpy the floor is or anything like that. What we're going to try to implement is a function called egg, which takes a number of floors and a number of eggs, and it's going to tell us the following. Guaranteed, so the minimum, guaranteed sufficient, number of trials necessary. To answer what I'm going to call the question, which is what's the tallest floor you can drop an egg from without it breaking. So we're going to write a function which you tell it how many floors you have, how many eggs you have, and it will tell you what's the smallest guaranteed sufficient number of trials that you need. Because, if there's 50 floors and you've got a zillion eggs, you can definitely answer the question with 50 experiments. Just drop it from each floor, right? But what's the best possible solution? And you might get lucky. You might do 2 experiments. This one it survives, this one it cracks, and you're done. Yeah?
Would the code for figuring out the maximum number be like the high-low?
Yeah, high-low is a piece of this. But it's a little different, right? Because if you guess wrong, the game is over if you run out of eggs. So suppose you only have 1 egg, and you got 50 floors in your building. What does your first experiment have to be?
Floor 1?
Floor 1, because if you drop from floor 2 and the egg breaks, you're out of eggs, you don't have an answer. You don't know if it would have survived floor 1. So your first experiment has to be floor 1. If it breaks, you're done. But if it survives, now you got to try floor 2. So if you only have 1 egg and you got 50 floors, it's going to take you 50 experiments. On the other hand, if you have, say, 6 eggs, you can play high-low. You can start right in the middle, and if it survives, go halfway between there and the top. If it breaks, go halfway between there and the bottom. And if every experiment results in a broken egg, but you got 6 eggs, it's only going to take you 6 experiments to get down to 1 floor, you can do that. So the more interesting case is when the number of eggs is bigger than 1 and less than the log of the number of floors, and then it gets interesting. Did you have a question or comment?
No, I was just gonna say, like, if statement says, like, the number of eggs is greater than 4.
Yeah. All right, so we can define the answer to this recursively. We don't have enough minutes to do this right now, but we will do this tomorrow, and it'll be posted on PA5, and I did go through it in the previous section, but let me just give you the base cases. So egg of floors, eggs, equals 0 if floors is less than or equal to 0. 1 if floors is equal to 1. So if there's only 1 floor, it doesn't matter how many eggs you have, it takes 1 experiment. Just drop it from the first floor, see if it survives or not. It's floors if eggs equals 1. Right, because you have to start from the first floor and then try the second and the third. In the worst case, you're going to have to get all the way up to the top floor and find it survives all of those. Otherwise, we're going to define it recursively in terms of the egg function. Okay, so you can see that at the end of the previous lecture or on PA5, but we'll go through it tomorrow also. But if you're dying to know, you can look at the video. All right, so we'll define this recursively tomorrow, and then we'll talk about the details of PA5. PA5 is really just writing this egg function, and then a really simple main program lets the user type in number of floors, number of eggs, and it just tells you how many drops are sufficient. All right, so we will do that tomorrow. Have a good afternoon. I will see you then.